Okay. My name is Sebastian Kreuzer. I'm a PhD candidate from TU Darmstadt working at the Scientific Computing Lab. And I'm going to present a joint work that we have done with Marta Garcia's lab at BSc. And this will be about a compiler-assisted workflow for efficiency-guided selective tracing. And I'll get into what that entails exactly. Right. So as you all know, the size of the HPC system continues to increase over the time, making performance analysis and especially tracing sometimes quite arduous, especially if you consider full-scale tracing, where just the number of ranks, the number of data that is recorded creates very large data volumes, and this bit can become prohibitively large to post-process and do analysis on. On the other hand, if you switch to smaller runs and trace them, then this may not be representative of certain behaviors. And if there's nonlinear performance behavior in some aspects, that may not be captured. However, in theory, you don't have to measure everything in a full run for a trace, because usually you're interested in specific hotspots that are problematic in terms of performance. And so the analyst is normally only interested in some parts of this huge trace data. Okay, so how can we deal with this exploding trace size issue? There's various ideas how to deal with that and various solutions. One thing is you can rely on post-processing. So you record the whole thing, but then apply cutting and filtering mechanisms to reduce the full trace to a smaller representative, smaller trace. However, the issue is there that you still have to first, create a big trace. And if you are interested in different parts, you have to find out where to find them and how to do this cutting and filtering. Another option is doing trace compression, and there's a lot of research on that. And that's definitely one interesting path. The other idea is doing direct online or in situ analysis. So instead of recording the full trace dynamically, you have some kind of runtime system that decides what it wants to record. And that can be very effective too. And there's a lot of work on that. But the issue there is that sometimes you don't really know what is important and what is not important. So you can't really go back once the trace is recorded, and everything we have not recorded is not available. And what I want to focus here is the concept of selective tracing. As a broad definition, selective tracing means restricting data collection in selected parts of the execution. So instead of doing a full trace, you restrict data recording along 3 axes. So for one, there's the structural axis, or where to record data. And that is usually defined by a configuration of instrumented code regions. And by adjusting these instrumented regions, you can adjust that structural axis and control it. But then there's also the temporal axis, so deciding when to record these regions. Because a lot of times, let's say you have a scientific application that runs a simulation with a time-stepping loop, then maybe you don't want, 10 or 100 iterations of the same loop. But a lot of times it's sufficient to have like one representative invocation of this loop. Finally, there's the detail axis. So what to record, and this refers to the kinds and detail level of the performance data, which can be, let's say, hardware performance counters or parallel programming model events for MPI and OpenMP, and you can adjust the data collection on that level. So let's look at the current state of performance tools and how they support selection on those levels. So here I've looked at SCOP, tau, and X-ray. I haven't included any sampling-based tools here because they don't really cover that structural axis. And then it's also difficult to introduce all other temporal or detail level filtering. So we're focusing here on instrumentation-based tools. So looking at the structural axis, there's usually quite a bit of configurability in terms of instrumentation. So for example, SCOP has compiler instrumentation, and you can configure that via filter files. And there's auxiliary tools that help you to change the instrumentation based on collected data. Other options are source annotations, or for example, tau and X-ray also support dynamic binary instrumentation via dyn-ins. So there's a lot of option there. When looking at the temporal axis, there's not so much support on this side. So for tau and X-ray, the only option is to go into the source code and insert an API call saying, okay, start measurement here, stop measurement here. For SCOP, that's actually the only of those tools that has more configurability. You can define a file that says, okay, for this region, I want to record invocation n. Then finally, on the detail axis, there's again not so much like direct control for the user. So for SCOP and tau, you can turn it on and off, but there's nothing in between. And also for tau specifically, you have to go into the source code to control it. There's no runtime control system. For X-ray, there's one more detail level you can choose from, and that's burst mode, where instead of having all of the normal MPI and OpenMP events, you get a summary over a certain burst length. Right. So we are looking into how to maybe enable a better workflow for such tools, and especially regarding to these three axes of selective trace control. And we identified 4 key challenges. So first, there's the instrumentation challenge. So you want to have a reasonable granularity, and also you want to manage the overhead. So just instrumenting everything is not feasible in most cases. Then secondarily, there's a temporal control challenge. So as shown in the established tools, there's not a lot of support for this. And we were looking into making this more user configurable without having to modify source code, for example. Then there's the aspect of aiding the user in the decision making. So there's not really a lot of infrastructure based around this idea of selective tracing. So you can use the available methods to restrict the recording. But how to get to this configuration that makes sense for your program and for your use case, there's not a lot of explicit support there. And finally, the issue of the visibility gap. If you only have this on-off mode, then this hides spurious issues or degradation over time, which can happen, for example, if load imbalance or something like that creeps in over time. Right. Then our approach was to build an end-to-end toolchain that uses compiler support to address these challenges. And we are trying to build mostly on top of existing tooling infrastructure to be able to use the existing measurement tools, but extend that with analysis and control systems. Right. So for the instrumentation part, what we introduce here is a selective instrumentation method that uses a global call graph analysis and couples that with dynamic filtering to get a configuration that is low overhead and covers all the important hotspots. For the temporal control, everything is handled in the runtime system using a multi-fidelity approach. And I will get into that, how that is modeled later. Specifically here, we don't want any, we don't want the user to have to change or annotate the source code. So everything is configurable. Then on this decision-making front, we base this tool chain around a two-phase workflow where we first generate a profile like you would do in a lot of cases, and then run a semi-automatic selection based on parallel efficiency metrics from this profile. And to deal with the issue of the visibility gap, we have this multi-fidelity approach where we expose tool-specific measurement detail levels and expose that to the user. Right. As mentioned, we use a two-phase workflow that kind of mirrors how a typical performance analysis often goes. So starting from a profiling run and then going to a trace once you have a sensible instrumentation. So first we have this profiling stage where we generate the efficiency metrics and we also fine-tune the instrumentation. And then in the tracing phase, we selectively trace based on these profiling results. The core feature of this workflow is the configuration stage in both phases. So in both phases, the user can submit a query that tells our selection system what aspects should be considered. And based on that, the measurement config is generated. So in the first profiling phase, we run this query based on an annotated static call graph of the program. And in the tracing stage, we run on a dynamic call path profile that is annotated with the efficiency metrics. And as the underlying tool, we are using the compiler assisted performance instrumentation, short CAPI tool. This is a tool we have developed here at TU Darmstadt for this purpose. Kind of one of the central ideas here is that we want to make this as frictionless as possible for the user. And for this reason, we have a single binary workflow. So we build the program once, put everything in there that we need, and then don't require source modifications, don't require recombinations to go through the two phases. And one of the key technologies here is LLVM X-ray. We use that for adaptable instrumentation. Okay, a little bit more detail on the two stages. So on the left here, we have the profiling stage. And we start out with our binary that has been instrumented, and also we get an annotated static call graph from that. Then the user puts in a query. The user puts in the query, and our selection system generates a measurement configuration, which is then passed during the profiling run to the runtime system, which instruments the application accordingly. And I've marked some key components of the runtime system here. One, this is the X-ray instrumentation system. Then we have a dynamic filtering system to limit overhead, and also a validation system that can detect and to an extent fix defects in a static call graph that may affect the results. So resulting from that, we get an annotated call path profile that has parallel efficiency metrics generated by the TELP profiling system. And based on this, the user can write a query for the selective trace configuration. And the CAPI system takes this query and the dynamic call profile and generates another measurement config, which is then used for the tracing step. And in this step, we use extra for tracing, although we have looked into expanding this for different client tools, so SCOP and also NVIDIA Insight Systems. Here again, on the runtime side, we have the X-ray instrumentation for instrumentation, and then a system that handles the selective tracing model and reads the configuration given by the user. So now I want to go through some of the key components. So on the top here, I'm showing where we are in terms of build, profiling, tracing stage. And so let's first look at how we prepare the binary to enable this toolchain. As mentioned, usability is critical here. So we try to hide all the complexity behind the compiler wrapper and embed required data directly into the binary, so we can load it at runtime and also look into it statically, but we don't have to manage like additional configuration files and that kind of stuff. So here we have a situation where there's one executable and also shared library. So first looking into the aspect of LLVM X-ray. So X-ray is a feature of the LLVM compiler that enables runtime configurable instrumentation. How it works is it inserts patchable so-called knob slats. So these are just placeholder instructions at possible instrumentation points. And these are off by default, so do nothing, but can be toggled dynamically. So at runtime, if I decide I want to measure a specific region, I can tell the X-ray system to patch this specific instrumentation probe, and it will insert a profiling call at the reserve point by overriding the instructions there. And the advantage of the system is that there's near zero overhead or not really measurable overhead when inactive. So you can have a full instrumentation, but measure nothing without any overhead. And on the other side, I can decide dynamically if I want to change the instrumentation. I can disable these instrumentation points without having to recompile or restart the application. And we have extended this feature previously with shared library support. So how that looks in the binary, we have this ELF section with the X-ray slats. Then there's an X-ray runtime linked into there, where we can tell this runtime which functions to patch. And also in the shared library, we have the same thing mirrored. So we have this list of X-ray slats containing the instrumentation points. And we can tell this shared library also where to insert these points. Right. Then the second important aspect is the whole program call graph that we insert. So we use a tool called MetaCG to generate a call graph at link time, and we directly insert it into the binary for later processing and also for runtime loading. And this is used for the static instrumentation selection we do at the start. And we also can use it for runtime validation purposes. So as I said, this is extracted at link time and then put into the elf section, and also annotated with static code metrics. So based on these, we can make decisions on where to instrument. Right, then kind of on a more general level, we have several runtime libraries in there. So each shared library has its own like small DSO local runtime, which tells the main management runtime where to find the individual list of patchable functions and the partial call graphs. Then the main management runtime manages the patching of X-ray slats. It also performs call graph validation and forwards the region events. So once we have patched selected functions, it forwards the events that we receive to a tool abstraction layer, which then informs the tracing or profiling tool about these events. And also when we trace, it implements these selective tracing semantics. Okay, now I want to go on to more of how the workflow is organized and some of the aspects there. So yeah, we rely on CAPI for static instrumentation selection. To start, based on this static whole program call graph generated by MetaCG. And CAPI is kind of built around custom query DSL. So you write a query that combines a bunch of predefined selector modules that have different semantics, selecting functions based on different features. And you combine these in this using this query DSL to build a configuration. And I'll show an example of that in a second. But these queries can be based around just general prior knowledge of relevant code sections, but also function local metrics such as instruction counts, static flop counts, and loops, and that kind of metric. Also, we can select based on call paths, so select certain callers and callees up to a specific depth. And there's some derived metrics we can use. And one that we have used specifically for this selective tracing approach is the inclusive statement count or inclusive instruction count, sorry, which gives a general good first approximation of a sensible first instrumentation. So looking at the example on the right here, we have a very simple call graph of functions main, init, solve, log, and dgem, annotated with local instruction counts. So what the inclusive instruction count does is just look at all of the reachable functions from each node and sum up the number of instructions. So for a function that doesn't have any callees, it's just a local count, for example, for log here. And for the others, it's the sum of the subtree that's reachable. By defining a selection threshold, you can then exclude functions that have too few instructions and thus exclude them from measurement. So down here, I'm showing a basic query that uses this inclusive instruction count with the threshold of 500. To kind of show maybe a more extended example, there's one here with a similar call graph. In this case, we have maybe a more a specific measurement objective or more information about the code. So in this case, we want to combine the inclusive state or instruction count with more prior knowledge. So for example, we can also select based on MPI calls. And this is what the query down here does. So each of these assignments creates a partial selection pipeline where individual selector modules can be instantiated and then combined. And we have different operators. The single bar is just a logical, is a combines two sets, and the bar combined with the greater than symbol is a filter operator. So by chaining together the selectors, I can filter down from by using multiple individual selector modules. And finally, in the last line, line 5 here, there's the instrument directive. And using that, I can control which is my final pipeline to be used for the selection. Right. So I talked a little bit, or I mentioned the core graph validation aspect. And that's kind of important when working with static analysis in this case, because due to dynamic language features, there's often missing edges in the static core graph. And this can affect the downstream analysis. There's an example on the right here. So there's this struct solver config, which has a function pointer, which is called then during runtime. But the compiler doesn't know or can statically not know the exact call target there. So when building the static call graph, this solver function call will not be captured or must be heavily over approximated because we just don't know what callie is. And what we've done here is introduce a validation system based on the prior work. What we do is we instrument these indirect calls, passing the name of the caller function and the function of the callee, which we then resolve at runtime to build a dynamic graph of missing edges. At the end of execution, we merge that with the embedded static call graph, and we can then rerun the static selection query to find out if there's a difference in the result of the selection. And normally, in a lot of cases, functions pointers like that are not super relevant to the results of the query, but in some cases, there's some critical paths in the call graph that are missed otherwise. And using this validation system, we can notify the user if something like that happens, and the user can then choose to rerun the selection and repeat the profiling step with the fixed call graph to get the full picture. Then finally, on the profiling side, we have a dynamic filtering system. So the static selection alone is often not sufficient to fully control overhead, or sometimes there's a few functions that kind of slip through the gaps and then introduce like high amounts of overhead. And what we have done here is adopt the throttling approach introduced by Tau. What Tau does is enable the user to filter out functions automatically at runtime after recording a certain number of invocations, and then just looking at the average execution time of these functions and filtering them out if they are below a certain threshold. In Tau, this filtering is done on the runtime handling system, on the event handling system, so there's still residual overhead. What we can do with our system using X-Ray is dynamically unpatch these functions, which is thread safe and therefore does not incur any synchronization blocks or something like that. And this then fully eliminates residual overhead. Okay, now to the tracing side. So we have a kind of basic selective tracing model that we apply in our system. And the yeah, very basic approach is to have a trace configuration that assigns measurement detail levels to specific invocation ranges, which is kind of similar to what score P does. But yeah, we have this added concept of measurement detail levels to build on top of that. This model is kind of built around that when you go up in the call stack. So if a function is recorded on a certain level and you go one level up, so this function calls another function, then you can get more detail, but not less. And this is kind of to ensure that the final trace is in a sensible state. So for X-ray, we have these measurement levels here. So the lowest level is just record nothing. Then there's the annotate level, just recording the function entry and exit timestamps. There's the burst level that corresponds to the burst mode of X-ray. The full mode just records everything in full detail. And then as the highest level, we have this force off mode, which just enables the user to always choose to completely turn off measurement in specific cases. So showing you an example here of this model. So on the right, you can kind of see the instrumentation directives that were used for this configuration. So we have functions bar, foo, and main that we want to consider here. For bar, we record it in the detail mode for the first invocation, and then off in the second. For foo, we only record the one iteration in detail in the detail level, and main we only record in burst. So starting off here, you can see the kind of the stack of invocations over time, and then below that the resulting level during the trace. And so when the program enters the main function, it starts off in burst mode because main is configured as being recorded in burst. Then foo is recorded foo is first not recorded, or the measurement level doesn't go up because only the second iteration of foo is recorded in detail. So when entering foo, there's no change here. However, when entering bar, this is the first invocation of bar, and we switch to detail level since detail is higher than the current burst level. Then we go back to the burst level for foo and the rest of main. And once we reach bar, sorry, there might be a mistake here. Actually, because we are already in burst, bar should be recorded also in burst mode here. That's a mistake in the figure. Right. So let's look at how to configure this trace. So how to build these configurations. And you can do that by using a command line tool, but we also worked on a GUI to kind of visualize the profiling results, and then also enable the user to run queries interactively and look at the selections. So here's just a screenshot of a profiling result showing the efficiency metrics color coded. And then shown on the right side here, you can also visualize that as a flame graph. And then there's a built-in query editor where you can build queries and then run them interactively. And the GUI will show you which functions are selected. And we're also working on trace size estimation to kind of get immediate feedback on what the query does on the runtime level. Right. Then to kind of put everything together, I want to go through a case study we have done using the Rasiata code. I think Valentin Seitz, maybe one of the last few webinars, has introduced like an in-depth analysis of this code. Here, I just want to show how we can use this selective tracing approach to get a usable trace for this code. So yeah, I'm not going to go deeply into Rasiata itself. It's a space plasma simulation code with hybrid MPI-MP parallelism. And what we've done, we've built the code with our wrapper that instruments the code and inserts the static call graph, where the call graph has around 2,000 function nodes. So then we enter the profiling phase. We do an initial instrumentation selection based on the inclusive instruction count metric that I've introduced at the start. And we've looked here at how that changes based on the instruction threshold K. So obviously choosing a higher threshold of instructions will reduce the number of functions that are selected. And what can be seen here is that there's kind of a power law relationship between the threshold and the number of functions. So both axes here are in log scale, and on this in this kind of view, you can see almost like a linear decrease, which of course translates to more of a power law relationship. In general, there's not a perfect instruction threshold for every case. Kind of depends on how much detail level you want. However, we found in general the 1K to 10K threshold is the range that makes sense for most applications. If you want to be on the safe side, it's better to use a lower threshold, around 1,000, for example, and then rely more on the dynamic filtering. If you are more worried about like having a more coarse granularity and also limiting overhead more, then it makes sense, of course, to increase this threshold, but that depends on the application. Right. So here we've chosen the threshold of 10,000 for the upcoming profiling. And we're using dynamic filtering parameters of measuring functions 100 times before excluding them, and excluding those that are below 10 microseconds in runtime. And this is on a 4-node run. So we've looked at some different other tools to compare our profiling approach. And we've looked at SCORP in two configurations. First, using SCORP with the LLVM plugin for instrumentation without explicit filtering. And then also using a filtered variant where we generate dynamic filtering based on the SCORP score tool with the same parameters as above. Then we've also looked at tau. For tau, we've set a static instruction threshold of 1,000 and activating throttling. This is kind of I would say, beneficial configuration for tau because the number of function instrumented here is lower than for us. Also, the static instruction filtering that tau uses is on a function local level, so we don't have the global approach, and that can lead to some gaps in the call graph in the end. Then finally, we also looked at using TALP without explicit region instrumentation, which just gives global efficiency metrics without the individual function. So looking at the runtime results on the left, we see that with SCORP without explicit filtering, there's obviously a large initial overhead, which is to expected. When applying filtering, it goes down significantly, around 60%. For tau, we have around 23% overhead with throttling and this instruction threshold. However, the number of functions there is lower than in our case, and we were also not able to record a context-sensitive call path profile, but just like a flat profile. Then finally, for our Kirby configuration, using the inclusive instruction count metric, we have a 17% overhead, and that is actually quite close to just running TALP on its own, which is around 16% overhead, but we get the added results of the individual functions. In this case, we had 187 regions recorded with metrics, of which 10 were filtered out due to low runtime. Okay, now how do we build a query based on that? So in this case, we chose an objective to detect regions with subpar parallel efficiency and instrument them for one invocation to get like a detailed view of those functions there, and then record the rest in burst mode to get summary metrics for the rest. Then we also want to exclude the initialization phase and record that in burst mode as well. And finally, we want to annotate the regions for all relevant call paths, if not already included in the set. So this is the trace we came up with for this case. So first we find the functions that have type metrics attached from the generated profile, and then only consider the ones that are not filtered out. Then we filter by the parallel efficiency, excluding those that are below 0.4 in terms of parallel efficiency, and have a minimum useful time of I think that's one second. Yeah. Then we detect the initialization phase and select the JSON call paths and find the relevant regions from that. And in the end, we combine that to instrument some of the relevant regions in detail and the others in burst or annotation mode. Okay, looking at the trace that was generated with this. So first of all, we got around a 10x trace size reduction from around a gigabyte down to 90 gigabytes. And this is on 500 nodes. So on top here, you can see the annotations. So these are the region names generated by Kapi and instrumented. So at first here, we have the initialization phase, where this is kind of shortened here. And then the individual time steps. And below that, we're showing the MPI calls. And you can see that only for the third time set, we record everything in detail, which you can also see in the tracing mode below. So it shows you if we are in burst mode and in detail mode or just annotating. And below the MPI calls, we're also showing the average MPI call duration. And for that, we can also see that in regions where we only recorded in burst mode, we still get that information. So for the initialization phase, we don't have the individual MPI calls, but we have the summary of the call durations in bursts. Right. Then let's talk a little bit about future directions. So we looked at Vlasieta so far, at a few prox applications, working with OpenFOAM as well. But we definitely want to evaluate a wider range of applications. Another work in planned work in progress is Flang support. There's a request for comment on a discourse at the LLVM discourse at the moment to support X-ray for Fortran instrumentation as well. Currently, it's only for C and C++. So we hope to widen the applicability of that. Then we also want to extend X-ray or look into extending X-ray for custom region and loop instrumentation because currently it's only on a function level. And we are also looking into extending the selective tracing model. For example, there could be an extension to allow specifying hierarchical invocation ranges, saying something like first record 2 iterations of A within the first iteration of B. So instead of having everything on the global level, selecting these invocations based on the current call stack. Also, we are looking into extending the supported backends. So far we've mainly looked at X-ray for tracing, but in theory we can support different backends with our tool abstraction layer. We've already experimented with SCOP and also Insight systems for GPU profiling. If you're interested in maybe playing with this kind of toolchain, we have a container containing the development versions of these individual tools. And with those, you can play around and instrument code and run traces, and also reproduce the results shown here in these slides. Then that's it from my side. Thank you very much.
Yeah, thank you very much. Very interesting talk. Lots of interesting details. I guess there's probably a lot of questions. So far we don't have anything in the chat, but perhaps if someone wants to have a question, just unmute yourself and ask. So while people are thinking, let me ask like one question. Actually a very specific one. So I understand that some of the features like the throttling and other things are happening during runtime. So it's a dynamic change of instrumentation.
Yes.
But typically when you do this happens on a per process basis, isn't it? So if you run like on 500 nodes with 500 MPI calls, this has to be done 500 times in parallel. And so do you synchronize so that every process is doing the same thing? Or if not, how do you avoid inconsistencies?
Yeah. For the dynamic filtering, we do not synchronize just because that would introduce a lot of complexity and more overhead, and then kind of defeat the purpose. But we kind of accept that these kind of inconsistency can happen. And for the profiling tool itself for TALP, that can just handle that. So it will have events from some sites and not from other sites. But of course, you have to, when doing analysis based on these results, you have to look at, okay, if this was filtered in one rank, then of course you want to exclude the results from the other ranks as well. So at the end of the execution, we run like a global reduction of all the filtering results, and then exclude the things that were filtered on the per rank level.
I see. Okay. Okay. Any other questions from other people in the room? Okay. Looks like everyone is totally flashed by your extensive explanations, and they have to think about it. Yeah, I guess Sebastian is available per email or something if you have further questions in the future. So uh, if there are no further questions, thanks everyone for joining. Thanks, Sebastian, for this very interesting uh, talk, and see you later at some other pop webinar. Thanks. Bye
Thank
bye.
you.